All right, so let's get back into this problem. Okay, how much kilowatt hours per year was lost at each stage in the process? Generation, transmission, and distribution. Include the power plant and T&D losses. So I think we need to look at Amory Lovin's article to get at that. Scope of this problem is from the customer's meter to the power plant. So let's go back and look at that because he's going to we'll just use his numbers.
That was in week 6, right?
Week 6, yeah. Is it under resources or week 6?
Well, I'm not sure.
I'm going to check resources. System Prius, CPU. I bet it's under reading. Usually he's just got a little link there. What power? Legislation, proposed decision, CPUs. Okay, here's Lovin's right here. More profit, less carbon. Way to go, Amory. Documents, courses. Lovin's. Oh, I already had the copy right there. Okay, sweet. Sure. Okay, so there's my download.
So I'm assuming it's just this diagram that's a couple pages down. It's that thing.
Wow. Yeah, so I see, here's your power, and there's your transmission and distribution.
So you use the motor and...
Yeah, so everything else is, this is the consumer is all downstream of that. Yeah, exactly. Okay, so, okay, now here's one thing to think. We are not adding these numbers, we're multiplying them. Because if you'll notice, if you add 70 plus 9, now you're at 79. You add 10, now you're 89. You had 2, you're now at 91. You had 25, you're already up over 100. So when you multiply these numbers together, you get 91.7. Let's just verify that. Okay? Check it out. So 0.7 times, let's see, hang on. Let's do it this way. Yeah, 0.7 times. No, hang on. Let me think about this the right way. 30. I got to write it out. Breaking my own rules. Breaking my own rules. So we're going to start with 100, and we're going to lose 70% of it. So we got to multiply that by 0.3. So we would get 30% out. Now we're going to lose another 9%. So we're going to multiply that by 0.91. We're going to lose another 10% of that, so we're going to multiply that by 0.9, and and then we're going to multiply that by 0.98, then we're going to multiply that by 0.75, and then, so I'm just taking 100 minus each one of these numbers, 0.33, or 66, 67 actually, and then 0.8. So let's run those through the calculator. Okay, so 100 times, hey, come on. How do I clear this thing? Hello, clear. Okay. 100 times 0.3 times 0.91 times 0.9 times 0.98 times 0.75 times 0.67 times 0.8. There we go. Pretty close. So that's how he gets the 9.5. So that's the efficiency of the system. So less than 10% of the electricity actually makes it into the device once you've lost all this stuff. Okay, so let's go back to the problem. We're looking at so I'll write it down this way. Efficiency thermal equals 30%. And sometimes you might see 35%, but that's about right. And then efficiency T&D equals 91%, 0.91. Okay, so now we're slowly gaining information here. Let's go back to week 7. Unit 7. Next page. Reading. Third page. Problem 2. What are they? 3,000 hours per year. Got all that. Got it. Okay. How much energy was lost at each stage for both systems? All right, no problem. Let's go. I might have started this one. Let me see. Documents, courses, 214, week 7. Maybe. Let's just see how we're doing here. Okay. Wow. I might have already done the problem. I just want to go through the thought process here, though. So, 10,000 lights is the number coming in. Let's just double check all that. 10,000 lights. Incandescent bulb. 75 watts, is that what we said? 75 watts, okay.
18 for the LEDs.
Burn in hours per year, 3,000, got that. So these are just numbers that go in. I think what I'm going to do is make those yellow.
So the LED operating hours is 2250 because of the...
Yeah. So right now, this is just input. So the incandescent customer watt hours per year. So I've got the number of bulbs times the number of watts times the hours per year. So this guy, I'm going to put this in I'm going to put this in gray, as that's a calculated answer. Incandescent kilowatt hours per year. I just divide that by 1,000, fine, that can be gray. Incandescent plant, okay. So where is that coming from? So the plant, and let me show this down here. So the power plant efficiency, and I'm going to turn this into symbol, like that. Oh yeah, I love that. And now I'm going to do the same thing here. Control 1, font, symbol, cancel. What's going on? I don't need that. Let's just go up here. SYMBOL, symbol. Ding. Okay. So the power plant is 30% efficient. The transmission is 91% efficient. Okay, so this number, what I'm doing is looking at how much power is delivered versus how much is coming out of the plant. Now, I'm not 100% sure that's correct, so let's just do it pencil paper. Let's just do it pencil paper, because I know that, and here's how to do it. So efficiency, let's start with our equation. Efficiency equals energy out over energy in. And the only thing we have here is the energy out. So energy out equals the efficiency times the energy in. Now in this case, the energy, and what am I using? So let's change over to what we're here. I'm going to call this CUST, C-U-S-T. So I'm going to do energy CUST for customer.
Oh.
Yeah, dang it, I'm paying too much on customer. C-U-S-S-E-D. But we've got two different efficiency losses. We've got the efficiency thermal at the power plant, that's what's lost, times the efficiency, you know what, it's also thermal. Because when energy flows through a system, it's giving off heat. Mm-hmm. So but I'm still going to call it transmission and distribution times energy in. Now, let's go back to our Algebra 101, or 121. We know this, we know this, we know this. We don't know this. So let's rearrange the equation. So energy in equals energy, or sorry, let's go back a little bit. Tools, eraser, medium, tools, pen, chisel, energy, power plant, right? I think that's the way I had it here. Plant, or PP for plant. So the P is power plant. Now, we don't know energy power plant, so EPP equals energy CUST over thermal efficiency times transmission and distribution. So in this case, we know that the energy of the customer, we've already calculated that out in kilowatt hours per year. Let's do it in kilowatt hours per year. So 2,250,000. Over these two numbers, 30% efficient for the power plant, 91 for distribution. 0.3, 0.91. So let's do that with our calculator first. This is what you must do if you are an engineer or an engineering technologist. So let's start off the calculator. So 2250,000 divided by 0.3 divided by 0.91 equals 8241. Perfect. Okay. So so the formula that I've got in Excel matches what I just did by hand and with the hand calculator. So that's good. I'm going to call that green for good because I like that. Okay. The incandescent losses. Well, it's how much was made at the plant minus how much the customer used. Just subtract the two. The replacement cost was $500,000. I'm going to throw a little line in here. Just to, if you want to get fancy, and so you go ahead and get fancy with this. And I know it usually helps. Like, okay, I got this right. So incandescent. Did I spell that right? I don't think so. I don't think I did. I'm having so much trouble spelling lately. I'm such a slave to the spell checker.
Well, if I didn't have that, I'd just be gibberish.
D-E-S-C-E-N-T. D-E-S-C-E-N-T. Okay. I was off by one vowel. Incandescent. Perfect. Okay, so there's our losses, and this is kilowatt hours per year, lost as heat to the environment. Okay, but now we're going to come in with our 500K, and let's just put this guy in here. Insert, Control Y, and then this is going to be LED. Center, merge and center, cool. LEDs are run at 18 watts. Now I didn't put an occupancy up top, but it's 100%, so it's just multiplying by 1, so we don't have to necessarily bother with that. Power per bulb, that can go in as yellow, fine, just like the other one did. Occupancy, fine, that'll go in as yellow. LED customer watt hours per year. So now we're multiplying 10,000 times the 3,000 times the 18. There are 4 multiplicants to make the product. The 75 comes in, and there we go. Watt hours per year, and so I'll go ahead and put that in gray also, like I did up top. LED customer kilowatt hours per year, you divide by 1,000, fine, still gray. LED plant. So now let's double check. I took the customer per year and I divided by both efficiencies. So I've already done that once. Nice, done. LED plant. Cool, and I'm going to put that in green also because I'm happy with it. Okay, the LED losses were only 1 million kilowatt hours per year. Now, okay, so if let's just say you're the executive and you hadn't seen this stuff before, you're like, oh, the LED bulbs are 18 and the incandescents are 75. Let's just do some math. What are your losses? Well, 75 divided by 18 equals 4.1, or let's just say 4.2. So let's just do that. So equals 75 divided by 18. So you're like, oh, they're 4.1 times better. But if we do it this way, I don't even know what that is. Let's just get rid of it. Oh, that's a double check. If we do it this way, equals the losses divided by these losses. It's actually 6 times better. There's an occupancy deal in there, so there's some subtlety here in the accounting that would typically be lost if you were just glancing over this problem. Okay, now the carbon tax. So you're providing the same service to your customer. The customer is still, the 18-watt LED is providing just as many lumens as the 75-watt incandescent. It's got a better efficacy. The carbon tax, we're looking at $5 per megawatt hour. So I'm going to change that into the carbon tax. The customer cost is 8 cents per kilowatt hour. Okay, those are both yellows, and I'm gonna put both of these as blue because they're more or less, in my mind, those are physical constants. Those are things that just, happen in nature. You can't, it's physics, right. You know, unless you're going to violate Carnot's rule at the power plant, and unless you're going to violate Joule heating in the wires or come up with some superconductor, that's just where we are. Okay. Now, the annual savings in kilowatt hours, let's just see what that is. Let's just see how we got that. The LED customers are going to be charged for 405,000 kilowatt hours at their meter. Right. The incandescents, 2.25 million kilowatt hours at their meters. So there we go. Annual energy savings is across all customers. And let me just put this customer. This is at the meter. This is not at the plant. The annual monetary savings, this is also an output. I'm going to put that as a gray. Annual monetary savings, yeah. So your customer base is going to spend $147,600 less per year. Perfect. I'm going to put that in green. Okay. So let's see if we've actually made any progress here or not. How much energy was lost at each stage to the customer's meter. Well, that's how much in the LED, and that's how much in the incandescent. So we got that. Perfect. Nice. How much energy and money? Well, just answered that too. There's the energy, there's the money. How much total energy will be saved annually? Now let's see. Total energy, system energy, kilowatt hours per year. This is at the customer side. So what we need to figure out is, no, we've already, yeah, we figured it out. This is what the plant burns This is what the plant burns with the incandescent. This is what the plant burns with the LEDs. How much total energy in kilowatt hours will be saved annually?
What about the discount rate in like the program?
Yeah, we'll get to
Oh,
that.
that's for the.
Yeah. So the plant is going to save this much, equals, that's what they're burning at the plant, minus the LEDs. The plant is going to save 6.7 gigawatt hours. And this is kind of small potatoes too. These are not giant plants, are they? Watts, 10,000. What is this in watts? Mess up my sheet here a little bit, but I just want to figure this out. Power, watts, equals, burn hours per year. I just want to figure out what the average is. So this is going to be, how many hours per year? Let me do it over here. Equals 24 times 365. So power in watts equals 10,000 times 75. So if all of the, if they were all on, number, tink, tink, comma. Okay, we're only running at, yeah, it's only 3/4 of a megawatt to run all these bulbs, but they're not running all the time. Watt average equals this number times this, times this number divided by this number. It's the fraction of hours. We're only running 3,000 hours per year. There's 8,760 hours per year, so that's the fraction of the time they're on. So the average power is less than what the maximum would be. So it's it's a 1/4 megawatt. Okay, so it's not that much. Colstrip runs at 2 gigawatts full blast. Yeah, so it's kind of small potatoes, but it's just lights. Annual energy savings, kilowatt hours. So 6,758,242 kilowatt hours per year. So plant savings, green, I like that. How much total system energy, kilowatt hours per year? I'm coming up with 6,758,000. How much CO2 was saved by considering the system losses? Discussion board members look up and provide to class. Units of pounds per CO2 would be best. We should discuss this on the forum. Well, let's Google it. CO2 per kilowatt hour. Let's just check it out. Let's just do it by state. Air travel, home, home, select. Let's do Montana. Oh yeah. Heating type, electric. Tons of CO2. Quick method uses state average for annual rounds of CO2 per kilowatt hour. Okay. Now, does that make sense? I'm going to run. No, that doesn't make sense. So I was going to run my house. For 1 hour at 1 kilowatt. I only needed a pound of coal. Remember? I'm not going to pump out 7.2 tons. That doesn't make sense. Let's go somewhere else. Let's don't do the state thing. It's too complicated. Let's just go out here. EIA, they're pretty good. Different fuels, average. Okay, cool. Okay, this makes more sense. This is about right. 2 pounds of CO2 per kilowatt hour, because you're gonna burn that pound of coal to make the kilowatt. The oxygen comes in, so that's about right. So let's just go with 2 pounds per kilowatt hour. Okay, LBS CO2 per kilowatt hour. You know, times are changing quick. They really are. I think they're changing much faster than we even know. I really you look at these numbers like, oh my God, it's so much carbon. It's unbelievable. And we're giving it away. Solar City is gonna rocket.
What's Solar City?
Solar City, so Elon Musk, I got to take a side note, because Elon Musk, back in the 90s, started this little company called Zip2, which was basically when you're on the internet and you want to know where like the pizza is or the gas is, the grocery stores are, it's built in. So you don't flip through the yellow pages and go, gosh, I don't know where First Street is. I don't know where, the 10th Avenue is. Zip2 would allow you, would sort of obviate the need for the yellow pages. You would type in what you need, where you are, and it would tell you what's the closest place to go get your gas, groceries, etc. And then there was always controversy over who made the idea. But anyway, he was able to sell it, make some money, and he converted a lot of that into PayPal. So he started PayPal because it's just easier than, sit down, write your check, fill out your credit card, all this stuff. So it just made monetary transfer much quicker. They would take just a few cents per transaction, but they became millionaires very quickly with it. Also,
Elon Musk started PayPal.
Yeah.
I didn't know that.
Well, you don't, because he and a bunch of other guys did, and then what was that movie, man? Oh, who's the kid who claimed it was some spy movie where he said, "I am the Napster." I wish I could remember, but there's some show where this actor claims to have invented the movie, the program Napster. It was like an Ocean's 11 or something, or no, it was called The Inside Job, or the, anyway, they cut a hole in the floor of some building and steal a safe in Venice, and the safe goes in the boat, and the kid says, "I invented Napster."
I remember that.
And so his roommate, the legend was, he invents it on his computer, right? He writes the code, then he's so tired he falls asleep. And so his roommate comes in, puts the floppy disk into his computer, steals the code, and calls it Napster. Because the kid's napping, right? Anyway, so there's all this controversy, who started it. But, so, Musk was in on the ground floor of eBay, or not eBay, I keep saying eBay, PayPal. Because they they bought each other or whatever. And so he makes some money off of that, and then he starts SpaceX. So it's his dream from childhood to send people to Mars and not do it slow and governmentally and NASA and big budgets and red tape and all this crap. I mean, I've had friends that work for NASA. I mean, bless their hearts, they just gave us some money to build a rocket stove, but it's pretty clunky. The bureaucracy is just sick. So he starts SpaceX to launch commercial rockets into space, and they pull it off on a shoestring with a bunch of guys that, you know, well, anyway, I don't know all the stories. But then, you know, meanwhile, he starts Tesla, you know, starts making electric cars with a bunch of software programmers. You know, Glenn Kreisel has one. Here's a couple Teslas in town. And with the money that they made, I think like Google had to buy them, but, you know, Google's all about connecting, you know, time and space and efficiency as well with their mapping systems and self-driving cars. And that's really where the transportation grid is going. So meanwhile, he's like, how do I fuel these electric cars? Well, solar. I don't want to pay for coal and crap like that. So he starts another company called Solar City. They're now manufacturing PV panels in New York State so they can then, you know, power their electric car grid. And Solar City's at the point now where they've got enough money that they pay the installer and buy the panels, up front, and the homeowner doesn't pay anything. So no upfront capital cost, but the homeowner does pay over time, which brings us back to this problem. Okay, so CO2 per kilowatt hour, pounds of CO2 per kilowatt hour, we're looking at 2. Fine, that's enough significant digits for now. And we looked that up via, where'd we go? Where were we? I slept for 10 hours straight last night, by the way. I think that's why I went to bed at 8:30 and woke up at 6:30. Wow. So I was feeling like junk. It's amazing. I put little earplugs in my ears and okay, so that's the reference for that. So getting back to Learning Unit 7, how much total CO2 was saved annually, considering all the system losses? Pounds per CO2. I'm going to put that in as blue as well. It's kind of a physical constant, I think. I like that color blue right there. Okay. LBSC. Actually, let's do it this way. Copy, because I like that subscript. Pounds per year equals dink times dink, 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 control 1, number, no, yes, okay. 13 million pounds of CO2. That is a lot. For just like this little light bulb problem. Yeah. Sorry, Cole, you're going to die soon. I mean, we'll try to save you. I think we have the answer, but you're going to die. All right. Now, what's the next problem? Especially giving it away, $8, man. What the heck? It kills me. Okay, how much did the program cost the utility per kilowatt hour in levelized costs, where the costs are turned into annuity and divided by the annual savings? Also calculate the program's first cost, present value, kilowatt hours per year, estimate the total. Okay, we got the CO2. How much did the program cost the utility per kilowatt hour? Present value, program, cost per, okay, so what I've done here is I've just copied in my, I've I've copied in my handy-dandy financial functions that we spent a lot of time agonizing over. And I think the discount rate was 6%. Let's just verify that. Yep, I is 6. We're running for 8 years. And now let's see what this amount is. Where did that come from? $8,827. Let's see how these things are working. Okay, I think all these guys are functioning. I don't see where's that $800,000 coming from? Nowhere. Maybe it's just some made-up number. Let's go back to the problem. How much did the program cost the utility? Per kilowatt hour, where costs are turned into an annuity and divided by the annual energy savings. Oh. Now, okay, so the replacement cost was $500,000. Now, I think what he's asking for here is to take that 500 grand. Let's just put that in here. Equals 500 grand. Okay. Let's just say that's the present cost. And I don't like all those decimals on. Let's get rid of those. Control 1. Currency, dink, dink. 8 years. I'm looking at an annuity of 80 grand with money being exchanged at that rate. So if this is the present value, that's my annuity. And let's just double check that. I'm going to put that in green because that's the one I like. Let's just double check that. So if the discount is 0.001 and the years are 8, let's just say the years are 10. It's $50,000 a year, right? So it looks like it's working. Let's take that back to 6. Let's take this to 8. So it's going to cost us $80,000 a year if the $500,000 is annuitized. You could say, hey, here's 500 grand right now, but nah, I'll give you some time to pay it. So some investor is going to say, oh sure, maybe it's a light bulb company that says, start buying our light bulbs and just pay us $80,000 a year and we'll call it good. Now let's take this whole thing. Copy, paste, that. Okay, now the utility is going to make less money because the consumers did not purchase as much electricity.
Right.
Now we're getting into like what's going on inside the utility's brain here, I think, a little bit.
Right.
I think we're doing a little mind reading. Should we do this? Well, so the customers are going to save $140,600 per year equals well, this number. That's basically the, this is the annuity.
The annuity would be the 23,769.
Well, no, I'm trying to, this is how much the power company loses in revenue each year. So it's going to cost them that much per year. So they're basically losing this much now, if that makes sense. So they're losing 500 grand now if they actually spend it now, and they're going to lose 147,000 per year, which means they're basically shucking out another $916,000 now. So this little calculator, does all 6 calculations at once. So on the one hand, we're looking at this and this as a present to annuity, and then we're looking at this and this as a annuity to present. Okay. But let's see how the carbon part works out. And so we can convert this to what the question asks is cost of the utility per kilowatt hour. So how many dollars per kilowatt hour is it losing? So here's the, I'm not sure which kilowatt hour to use. Per kilowatt hour. Well, we can do it both ways. Cost per kilowatt hour. And here's what I suggest you do if you're confused, because honestly I'm a little confused right now. We'll do it for incandescent first. Equals, so dollars per kilowatt hours. And I'm looking at this from the demand side. Currency. We could actually do all 4 of them. I don't even care. So this is at the plant. And I'm just going to say this to the class too. If you're confused and you don't know what answer to give, just give all possible answers and one of them's going to be right. I just want to see that you're like thinking this thing. Seriously. Because what's going to happen, you're going to be the poor technician who's standing like with the board over here and the customers over here, and they're going to go, well, what if, well, what about, and you've already done it. You've done it all. So cost for the plant, because the plant's burning through more BTUs than kilowatt hours they're sending. So now let's do cost per kilowatt hours in incandescent customer. So in other words, I mean, it's fine to be confused, but the way out of confusion is just to work it and just keep working it. So dollars per kilowatt hours from the customer, and I'll fix that in a second. Let's move these down. Can't remember what they are, it's okay. Cost per kilowatt hours LED plant equals cost divided by LED plant. Yep. Cost per kilowatt hour LED customer equals cost. And this is in basically lost revenue because they're saving. customer. So let's make all these the same format. Control 1, currency. Pop out a few more sig digs, fine. Did I do that right? Wow. Let's just double check here. Triple, yeah, wow.
36 cents.
Yeah.
Kilowatt.
Doesn't seem right, does it?
Seems high.
It does seem high, doesn't it? Yeah, I don't know. Let's just see here. Yeah, so something's not quite adding up. This is why you do the whole thing and figure out what's wrong here. Maybe the right way to do it is so the plant, the customers saved this much money. So the plant basically lost that much money. Let's go back to the problem question. Yeah, I think this is just the answer. It's just what the plant saw. I think the rest is just kind of nonsense. So the plant is basically losing 2 cents per kilowatt hour. Because they're still making their BTUs, but they're not getting paid as much because the customers aren't using as much.
Right.
So I mean, it's actually, well, the whole thing's just more efficient, for gosh sakes. Okay, so I'm gonna put that guy in green. Okay, now let's do the final bit. Estimate the potential carbon tax savings for the utility. So and we get back to this issue, we're looking at $5 per megawatt hour. So let's put in a new, let's just put in a new line here. Let's just do the tax at the bottom. New line. Tax. IC. So the tax was going to be equal to, and that, what was the value? It was $5 per megawatt hour. So we're looking at dollars per megawatt hour. 5. Insert. Let's just do IC megawatt hour per year. Equals kilowatt hours per year divided by 1,000. Right? IC carbon tax. Equals dink times dink currency. Okay, $4,000. This is in dollars. Currency, $5. Nice. And now let's take these two guys, copy, paste. And this is kind of fun. If you haven't tried this in Excel, I'm going to highlight this and do Control H, which is find and replace. I'm just going to replace IC with LED. Replace all. Boom. Kind of fun. Yeah, close. So I didn't have to retype all that junk. So now we just go up here, and I'm looking at the LED megawatts. So that is, or kilowatt hours per year. So the LED kilowatt hours per year. From the plant, there it is. And the carbon tax is going to be plant times the $5. Okay, so they were going to have to pay 41 grand a year in carbon tax. Now they've got the LEDs in place. They're going to pay 7 grand per year. So now we can go back up here and jam that into our financial model. This stuff is fun. I mean, everyone's like, oh, 214's hard. If you nail this course and you can provide this for utility, you paid your salary. I'm sorry, but you have. You can just fire everybody else. Because these are big numbers. These are not even very big plants, and these are some salary figures. Okay, so what are we looking at here? We're looking at a savings in carbon tax, and $5 well, wait, no, it's not dollars per megawatt hour, it's dollars per, oh, it is. It's $5 per megawatt hour, okay. Jeez, that's still approximately zero. Savings equals dink minus, oops, minus dink, okay. So you're saving 33K per year. So now we're looking at, so this is bulbs. This is kilowatt hour charge, right? And this is carbon. Control U, Control U, Control U. So the annual savings equals 33,000 bucks. Annual savings. Okay, so now what we're looking at is, I'm just going to call this the net present value of proposal. So this equals, so the plant is going to, the utility is gonna, so they're gonna save $33,000 per year in carbon tax. So that's gonna save them that much. This is how much the utility is gonna make. They're gonna lose this much because they're not selling as much electricity because they don't have to because the light bulb is more efficient, right? So the 200 is in the red, it's in the positive. The 900,000, sorry, they're going to lose that, minus also the present value, which is 500,000 if we scroll the money up front. So the utility is going to lose $1 million. Let's see what happens if we play with the carbon tax. Let's just make it 30 bucks. They still lose. Let's make it 50. Now they win. So that's why the utility, unless you make it hurt hard enough, they don't start to win.
Right.
So it's an interesting problem. Mm-hmm. It's a really interesting problem. I like that. I think that's it, right? Could add the utility value for not burning coal. Fuel savings, you'll have to need to look up the price of coal. Oh, I see, so we never really said, we didn't look at the utilities cost of burning the coal.
Right.
We didn't look at that at all. That's easy enough to do. Because they gotta buy coal. Well, buy it from Montana, $8 a ton. Well, I'll let you guys work on that. But this is a really good problem. Round and round. Okay, I'm gonna save that. And, I don't know, I think I'm gonna call it good. Unless, do you have anything else, Joe? You good?
No, I gotta
Okay.
get going anyway.
Okay. That was an hour, man. That was an hour of power, literally.